time travel has captivated our imaginations for generations. From H.G. Wells' The Time Machine to the adventures of Doctor Who, these stories have woven a rich tapestry of what could be possible if we could control time itself. In fact, over 50% of science fiction movies and TV shows explore themes related to time travel, making it one of the most popular concepts in the genre. Consider Back to the Future, where Marty McFly travels back in time to prevent his parents from breaking up. This plot not only entertained millions, but also sparked countless discussions about the implications of altering past events. The allure lies in our curiosity about what we could change or learn if given such power. As we dive into this topic, let's explore how physics might just hold the key to unlocking these temporal mysteries and unraveling paradoxes that have puzzled us for decades. At the heart of our exploration into time travel is Albert Einstein's theory of relativity. This groundbreaking theory introduced us to the concept of time dilation, where time moves differently depending on your speed and gravity. Consider this. If you were traveling at 90% the speed of light, which is about 270,000 kilometers per second, every hour for you would be equivalent to nearly 2 hours back on Earth. This isn't just theoretical. Atomic clocks flown aboard high-speed aircraft have shown slight differences compared to their stationary counterparts when returned to Earth. The implications are profound. If we could harness this effect, time travel might not be so far-fetched after all. Next up, let's delve into how these principles affect our understanding of temporal paradoxes and the challenges they pose in theoretical physics. Time dilation isn't just a theoretical concept, it has real-world implications. Consider GPS satellites orbiting Earth. These satellites experience time differently due to their high speed and altitude compared to us on the ground. In fact, without accounting for this effect, your GPS could be off by several meters every day. The difference might seem small, but over time, it adds up significantly. Take a satellite moving at about 14,000 km/h. Its clock runs slightly faster than ours due to special relativity. However, general relativity comes into play too, as the satellite's weaker gravitational pull slows down time relative to Earth's surface. The net effect is that GPS satellites' clocks gain about 38 microseconds per day compared to our clocks on the ground. This might sound insignificant, but in terms of navigation accuracy, it makes a huge difference. Understanding these nuances ensures your maps stay accurate and reliable. As we continue, let's delve into some of the paradoxes that arise when we start thinking about actually traveling through time. Causality is a fundamental principle of our universe, where every effect has a cause. In time travel scenarios, this concept gets incredibly tricky. Consider the grandfather paradox. If you go back in time and prevent your grandparents from meeting, how could you exist to go back and change events? This paradox challenges the very fabric of causality. Take the case of closed timelike curves proposed by physicist Kurt Gödel. These theoretical paths through spacetime allow for loops where an event can be its own cause. Such a scenario would mean that causality, as we understand it, breaks down, creating a temporal paradox. Understanding these challenges is crucial because they not only test our theories about time, but also push the boundaries of what's possible in physics. As we delve deeper into these concepts, we'll see how quantum mechanics might offer some surprising solutions to these puzzles. Closed time-like curves are a fascinating concept in theoretical physics that suggest the possibility of time travel. Essentially, these are paths through spacetime that loop back onto themselves, allowing an object or person to return to their starting point without violating any known laws of physics. Albert Einstein's theory of general relativity actually allows for such structures under certain conditions, though they have never been observed in nature. One striking case is the Gödel metric, proposed by mathematician Kurt Gödel, which describes a universe where closed time-like curves are possible if space is rotating. Imagine a cosmic merry-go-round spinning so fast that it warps spacetime enough for these loops to form. While this model doesn't reflect our actual universe, it's a powerful thought experiment. These curves raise intriguing questions about causality and temporal paradoxes. How could you interact with your past self without creating contradictions? This leads us into the complex world of self-consistent histories and alternate realities, where every action has a predefined outcome to prevent paradox. As we delve deeper, we'll explore how these theories might shape our understanding of time itself. The grandfather paradox is one of the most intriguing temporal paradoxes. Imagine if you could travel back in time and somehow prevent your own grandfather from having children. This would mean that your parent wouldn't exist, which means you wouldn't be born either. But if you weren't born, who prevented your grandfather from having kids? It's a loop that defies logic and creates a paradox where the very act of traveling back in time alters the timeline in such a way that the original event could never have happened. Consider the movie Back to the Future, where Marty McFly accidentally prevents his parents from meeting. The consequences are drastic, showing how altering past events can ripple through time with unforeseen outcomes. This paradox challenges our understanding of causality and raises questions about the possibility of changing history without creating contradictions. Understanding these paradoxes is crucial as we delve deeper into the science behind potential time travel mechanisms in our next segment. Quantum mechanics opens up a fascinating realm where time travel might just be possible. Consider how quantum entanglement allows particles to instantaneously affect each other, no matter their distance apart. This phenomenon hints at connections that could potentially span across time itself. Another key concept is the many worlds interpretation, suggesting every quantum event creates multiple universes. If true, this means traveling through time wouldn't alter a single timeline, but rather create new ones. Picture this. If you went back in time and changed something significant, instead of altering your original timeline, you'd end up in an entirely different universe where those changes already exist. These theories suggest that while the practicalities remain elusive, quantum mechanics provides a theoretical framework for how time travel might work without causing paradoxes. As we delve deeper into these concepts, we'll explore how advanced technologies could one day harness these principles to make time travel a reality. Quantum entanglement might just be the key to unlocking time travel. Imagine two particles that are so deeply connected, they instantly affect each other no matter how far apart they are. This phenomenon was famously referred to by Einstein as spooky action at a distance. Scientists have tested this with photons sent over distances up to 1,200 kilometers and found that the entangled pairs remain synchronized. Now, if we could harness this instantaneous connection across vast distances, it might be possible to extend it to time itself. Picture this. By manipulating entangled particles, we could theoretically send information or even matter back through time without breaking the laws of physics. This idea isn't just theoretical. Researchers at MIT have already shown that quantum mechanics can allow for time travel in a controlled environment. As we delve deeper into these possibilities, the next step is understanding how this might interact with other dimensions and parallel universes. If time travel were possible, it would challenge our very understanding of causality and free will. Consider the grandfather paradox, where traveling back in time to prevent your own birth creates a loop that defies logic. Philosophers argue this could mean our actions are predetermined or that multiple universes exist to accommodate each outcome. Take David Lewis's theory of modal realism. He posited that every possible world exists as a real universe, suggesting that any action you take in the past would simply create an alternate timeline. This raises profound questions about identity and morality if we could alter historical events. If we could change the course of history, who decides what changes are justified? The ethical implications alone are staggering. As we ponder these philosophical conundrums, let's also explore how time travel might affect our perception of reality itself in the next segment. Temporal paradoxes have fascinated audiences for decades, often explored through science fiction. Consider Back to the Future, where Marty McFly prevents his parents from meeting, threatening his own existence. This is a classic example of the grandfather paradox, where actions in the past could prevent your birth or existence. Another striking case is the TV series Doctor Who, featuring the character River Song, whose relationship with the Doctor creates a complex loop of events that defy linear time. These stories illustrate how altering the past can lead to unpredictable outcomes and logical inconsistencies. In real-world physics, the concept of closed time-like curves in general relativity suggests that time travel might be theoretically possible under certain conditions, but it opens up a Pandora's box of paradoxes. Understanding these paradoxes helps us explore the limits and possibilities of our universe. As we delve deeper into the mechanics of time, we uncover how these fictional examples mirror scientific theories. The concept of time travel isn't just a matter of bending space-time. It's also about energy. Consider this. To warp space-time sufficiently for time travel, you'd need an astronomical amount of energy, far more than what our current technology can produce. Scientists estimate that the energy required could be on par with what the sun radiates in millions of years. Take the Alcubierre drive as a theoretical example. It would require negative mass and exotic matter, something we haven't even figured out how to harness yet. Picture this. If you needed a planet's worth of energy just for a brief moment in time travel, that gives you an idea of the scale we're talking about here. The vast energy requirements make time travel a challenge not just of physics, but also of engineering and technology. As we delve deeper into these challenges, it becomes clear why temporal paradoxes might be the least of our worries when it comes to practical time travel. The future of time travel is still largely speculative, but some scientists believe that wormholes could be our key to traversing through time. According to physicist Kip Thorne, if we can harness and stabilize these theoretical shortcuts in space-time, they might allow us to send signals or even objects into the past or future. Imagine a world where instead of taking years for a spacecraft to reach distant planets, it could instantaneously appear there via a wormhole. While such technology is far beyond our current capabilities, advancements in quantum mechanics and general relativity could make this a reality someday. Looking ahead, consider how time travel might revolutionize fields like medicine or climate science. Picture this. Doctors could access future medical breakthroughs to treat diseases today, or climatologists could predict extreme weather events with pinpoint accuracy. These possibilities are not just the stuff of sci-fi, they hint at the transformative power that mastering time travel could bring. As we continue exploring these concepts, one thing is clear: our understanding of the universe and our place in it will forever be changed. Time travel isn't just a topic for physicists, it's also a staple of pop culture. From H.G. Wells' The Time Machine to the blockbuster hit Back to the Future, time travel has captivated audiences for over a century. Consider how Doctor Who, with its 60-year run, has become one of the longest-running science fiction programs in history. In fact, it has inspired countless other shows and movies, proving just how deeply ingrained this concept is in our entertainment. Take the recent success of Tenet, which grossed over $362 million worldwide, demonstrating that audiences are still fascinated by the paradoxes and possibilities of time travel. This widespread appeal makes it clear why understanding its scientific underpinnings is so intriguing. And as we dive deeper into these stories, we'll uncover how they often reflect our own hopes and fears about what might happen if we could really change the past or glimpse the future. The challenges of time travel are vast and complex. For one, there's the issue of energy requirements. Creating a wormhole, for instance, would need more energy than our entire planet can produce in its lifetime. Another challenge is the potential violation of causality, leading to paradoxes like the grandfather paradox, where changing past events could prevent your own existence. Consider also the technological hurdles. We haven't even begun to harness quantum effects at macroscopic scales necessary for such feats. Even if we could travel through time, the butterfly effect suggests that minor changes in the past could have massive and unpredictable consequences in the future. These are just a few of the obstacles standing between us and temporal journeys. As we delve deeper into these paradoxes, it becomes clear how intricate and daunting the journey to mastering time truly is. As we look to the future of time travel research, scientists are increasingly focused on quantum mechanics and general relativity. Consider how researchers like Igor Dmitriev at Nizhny Novgorod State University have explored wormholes as potential pathways through spacetime. With breakthroughs in technology and computational power, simulations of these theoretical constructs become more sophisticated. Take the recent advancements in gravitational wave detection. They could provide clues about the fabric of spacetime itself. One striking case is LIGO discovery of merging black holes, which might hint at the conditions necessary for time travel. While we're still far from practical time machines, every new insight into physics brings us closer to understanding the universe's temporal mysteries. As we delve deeper into these concepts, who knows what innovative technologies and theories will emerge? The journey ahead promises endless possibilities, and our quest for unraveling the secrets of time continues with renewed vigor. As we wrap up our journey through the mind-bending world of time travel, it's incredible to think that Albert Einstein's theory of relativity suggests that time is not a constant, but can be stretched or compressed depending on speed and gravity. Just imagine, if you were traveling near the speed of light, time would slow down for you compared to someone stationary back home. That's the essence of time dilation. Thanks so much for joining us today as we explored these fascinating concepts. If you found this trip through temporal paradoxes intriguing, be sure to hit that like button and subscribe for more mind-blowing science content. Until next time, keep pondering those cosmic questions that make our universe such a mystery wrapped in an enigma.